Ready. Okay, so good morning, everybody. I have lots of stuff that I can cover today, but I think sometimes that less is more. So I won't rush too much. I would try to do as much as I can, but without rushing, because there's no point in covering lots of stuff if it becomes incomprehensible. Any questions from yesterday? So one thing I want to say is that somebody emailed me to say, are there references? And yes, there are references. I've put in a slide with a few pointers to literature, and I will share the PDFs with the organizers later today. So you will have references as well for most of the things I've said if you want to follow them up. Yeah, that's about it. Okay. So today I want to go back and continue on the Bayesian cosmology side, more on the Bayesian side. Now that we have introduced cosmology, I want to talk a little bit about supernovae and hopefully the last hour about Bayesian model selection, model comparison applications to cosmology. Now, one question I have, Andres, how much, in which detail have you already covered MCMC methods? Yes, but it did everything from including practical questions and how to do it, etc. Okay, good. So it's already been covered, which is very good. So I don't need to go. Okay, great. And just do a quick reminder. Perfect. Okay. Let's see. Can you see the screen? Good. Let's see, where are we? Good. Now I want to move on to do a little bit more statistics. You remember that the upshot of what we said yesterday about the CMB is that if you use a clever parameterization, that's to say normal parameters, as I discussed, then you can approximate the parameter dependency of the power spectrum, the temperature power spectrum, almost as a linear function of the parameters. Essentially, think of this as a Taylor expansion of the response of the power spectrum to a change in cosmological parameters. That in turn means that we can then look at this problem from the point of view of a Gaussian linear model, which is nice because we can understand it from an analytical point of view. So let's go through the n-dimensional Gaussian linear model, where n here is the dimensionality of the parameter space. And so we have an independent variable, and we have a dependent variable, the response, y. And now the model, the simplest model in 2D, for example, if n is equal to so for n equal to, where a possible linear model, a simple linear model, would be the one here, where you have the response y or alpha plus beta xi plus noise. So it's just a linear model where the parameters are alpha and beta, and those are the slope, the intercept of your curve. So if you look at this plot here, it's a sketch of what you're trying to do. We got a bunch of Gaussian distributed data points, where the noise epsilon I is IID, by which I mean independent identically distributed, with a known variance sigma squared, and it's normal distribution. And what we are trying to do, we're trying to infer the slope and the intercept of a linear fit here. Okay, so our parameters theta are alpha and beta. And now, in general, you can always recast such a linear model in algebraic notation as follows. So here is an equation where we relate y. Y is the vector, is the data vector. Y is d-dimensional. So we go here. Y is d-dimensional. We've got d data points, and these are all the data points. Theta, the vector of parameters from 1 to n. So that's n-dimensional linear parameters. Epsilon is the noise vector, and F is a D cross N matrix of known constant which maps parameters onto responses, and it's called the design matrix. So for the linear model so just to give you a sense for what F is, in the linear model we had before, where the parameters are the slope and intercept, you can easily convince yourself that F, the design matrix, takes on this form. So if you multiply F of that form by the vector of parameters theta, and theta was alpha and beta, you will see that you will get something that looks like alpha plus beta x1, alpha plus beta x2, and so on and so forth until alpha plus beta xc. It's a vector, and that is equal to y, and y is just y is equal to y1 beta until yd. Let me rewrite this. y1 until yd is equal to f times alpha and beta, and that is just equal to that. So you can convince yourself that this is just a better way of writing the linear model down, okay, in a matrix notation. So in the linear model, then, the important thing to remember is that what we are fitting is, so we want to fit a function f of x, which is linear in the parameters. It's linear in theta, but the basis functions, let's just say the functions that the thetas multiply, need not be linear in x. In the case of the slope-intercept model, the functions here in the design matrix are just a constant and x. There's no reason why they should be linear in x. They can be any function of x. The important point of the linear model is that it is linear in parameters, not in the x variable. So that's the important point here. Linear model is linear in the theta j, not in the xi's necessarily. Okay, so then, for simplicity, we assume that the noise is uncorrelated. That's to say that the noise vector is coming from a normal of 0 mean, and with covariance matrix, which could be non-diagonal, but for simplicity, we can just take that each one of the measurement is uncorrelated with every other one. And so the covariance matrix C for the noise is a diagonal matrix with entries given by the variance of each measurement, which needs not to be equal, tau 1 to tau d. So under those assumptions, and because the noise is Gaussian, the likelihood function becomes a simple multi-normal function. And so the likelihood is given by the product of each one of the likelihoods. So it's an n-dimensional Gaussian, which is down here, where we are multiplying over j. So j is counting the data points from 1 to n, 1 to d. J from 1 to d. And then the exponent is simply a fancy way of writing down the Gaussian, where Aij is a matrix defined by the design matrix scaled by the standard error yi. Di is the measured data vector yi divided by tau y. So we're just a way of making those entries dimensionless as they should. So now the point is that the likelihood is Gaussian y, right? But because the model is linear, so that's to say the likelihood is Gaussian in the data. It is the data, the y's, that have Gaussian noise. But because the model is linear in the parameters, you can show with some simple algebra that you can recast the likelihood function as a Gaussian in theta, like that. So you can manipulate it in such a way that it's Gaussian in the parameters. So now it's a Gaussian in parameter space as well as being Gaussian in data space. And theta naught is the peak of the Gaussian, nothing else but the maximum likelihood value that you would obtain by the maximum likelihood estimator for the parameters, and is given by this expression here, where L is a square matrix n cross n given by A transpose A. And that's your covariance matrix. Or actually, that's the Fisher matrix. Remember, the Fisher matrix is the inverse of the covariance matrix. Fisher, so-called Fisher matrix is what goes into the exponent of the Gaussian. That's equal to covariance matrix minus 1. So the point of the linear model is that if you have Gaussian noise and a linear relationship, it becomes Gaussian in the parameter space as well. And so you get nice ellipses as you contours parameters, which is what we saw yesterday when we looked at the linear model. Sorry, when we looked at the CMB in the normal parameters, the constraints in parameter space were fairly Gaussian if we look at them in the right parameter set. So now, it's convenient to assume a conjugate prior. A conjugate prior is a prior that is from the same parametric family as the likelihood, and that usually leads to a posterior in the same family as well. That's to say that if the likelihood is Gaussian, and you assume a Gaussian prior, then your posterior is also Gaussian, because a Gaussian times a Gaussian is another Gaussian. It's very convenient to use a conjugate prior in this case. So for simplicity, we're going to choose a prior P, which is a Gaussian centered at 0 with a prior covariance matrix, or I should say prior Fisher matrix in this case. Well, the prior covariance matrix in this case given by P. And so because of what I just said, the posterior is also Gaussian, so the posterior is just the likelihood times the prior. And by plugging in the expression for the likelihood given before, multiplied by the prior, and doing the algebra, you will find that posterior is also normal, as you would expect, with posterior mean given by this expression here, where theta naught is the maximum likelihood value, and F is defined as the sum of the Fisher matrices. So F is the likelihood Fisher matrix plus the prior. And now, of course, from here we can see analytically that if we take infinity, in other words, if we take many, many data points, then L becomes much more sharply peaked than P. The likelihood dominates the prior, so the uncertainty, so the sigma for the likelihood is much smaller than the sigma of the prior in each direction from the space. That means that L, being the inverse of that, is going to be much larger than P in this metric sense here. And so in other words, for a large number of data points, posterior Fisher matrix F tends to the likelihood Fisher matrix, which is this statement here. And then this term here becomes unity, it becomes the identity matrix. And therefore, the posterior mean tends to the maximum likelihood value, as you'd expect. In the case where the likelihood is sharply peaked, the posterior must tend to the likelihood because the prior becomes irrelevant unless you are in some fairly sick, degenerate case. Okay, so this is to say that, by looking at the linear model, we can understand the Bayesian posterior simply in analytical terms without having to bother too much with a numerical MCMC. And then the CMB, as I told you before, is a very good approximation to this. Let me give you another view of that. Find it quickly. Here. You can see this is another example. This is WMAP data. You see the color coding and black lines are MCMC full numerical posterior distributions, and the red are a Gaussian approximation. And so you can see that the red ellipses are extremely good in approximating the full numerical posterior, to the point that it's really not worth bothering to do the MCMC in this case, because everything is so nice and Gaussian, so you can just use a Gaussian approximation. Okay. So now I want to talk a little bit about how do we get those constraints numerically, if you want to, even though you can do it analytically with a Gaussian case. And so, as I was telling you before, and as you have many times thus far, I expect in the school, the general solution to any inferential problem in a Bayesian sense is this. Simply write down the posterior distribution for the parameters given the data and any information I you might have about the problem as being proportional to the likelihood as the prior. So, of course, you will have to define the likelihood function, and that depends on the physics of the problem, on the instrument, on the details of the kind of inferential problem you are trying to work out. The prior sometimes is taken just to be flat, uniform parameters. As I said yesterday, this is not a choice to be made lightly. You have to be careful, attentive, and critical of uniform priors, especially large number of dimensions. But let's say that you have the likelihood and you have the prior. How do we evaluate the posterior then? So we can do analytical solutions like we just did for the Gaussian linear model. Also, we can use numerical methods such as Markov chain Monte Carlo, which is, as you know, a procedure to generate a list of samples from the posterior. So I already covered this with Brandon. I'm going to just quickly remind you of those aspects. I'll go fairly quickly because it's just a reminder, really. I know you've seen this already. So a Markov chain is then a list of samples, theta 1, theta 2, theta 3, whose density reflects the unnormalized value of the target density. A Markov chain in particular is a sequence of random variables with n plus 1 element. Only depends on the value of the previous element. And the crucial property is that it converges to a stationary distribution. That's to say, for large number of steps, that the stationary distribution does not change with time and matches the target distribution, the posterior. Of course, this is only, I remind you, asymptotic statement. It is true for number of steps tending to infinity, but of course, in practice, we always have only a finite amount of computing power, which means we have only the ability to gather a finite amount of samples. So then it's a question of efficiency and how do we ensure that our target distribution has been adequately sampled given the amount of computing power that we have, the amount of samples that we've been able to gather. And that's all art of MCMC, how to get those samples in such a way that they are sampling from the entire distribution, that they are converged to the distribution, that they are uncorrelated, and so on and so forth. So those are all technical questions that are very important. I cannot address them here because this is more about giving you a sense for the methods than the technical details of how to implement it. But I hope and expect it to think in the more practical parts of the story. Okay, now if we have the chain, if you have the chain, Markov chain, then you're done, because then you can do Monte Carlo estimates of all the quantities that are of interest to you. So, for example, if you're interested, say, posterior mean for your parameter theta, expectation value of theta under the posterior, the samples, the theta i's themselves, are drawn from the posterior distribution by construction. If your MCMC is working right, then expectation value is typically the mean of the sample, the mean value of the Markov chain sample. And equally, the expectation value of any function of the input parameter is typically the mean of the function value evaluated at the sample's location. Of course, there's more. You don't just have to compute expectation values and variances, standard deviations. You can, in fact, just as simply plot the entire distribution. Just plot what the distribution of the samples in a suitable way, and you access not only to the mean and the variance of the posterior, but to the full shape of the posterior. And so once you have found the posterior by Markov sample, you can report your inference by standard statistics, average, the mode, best fit point, the standard deviation, etc. You can report credible regions. These are, for example, a 68% credible region will be an interval containing 68% of your samples. And of course, there are an infinite amount of ways of choosing the 68%. And usually what is done, you would report the shortest interval containing 68% of the posterior probability. Remember, and again, I think this is just a reminder, credible region in a Bayesian sense does not have this thing as a frequentist confidence interval, although the two might be formally identical. For example, in the Gaussian case with uniform priors, confidence intervals from the likelihood are identical to credible regions from the posterior, two completely different things, as I'm sure I know actually Tom has covered. And so the frequentist confidence region is a statement about the number of times the true value is covered by the interval in a long sequence of repeated experiments, while the Bayesian credible region is conditional on the observed data, and it tells you something. It tells you what is the probability of the true value of the parameters included in your given interval, given the one realization of the you saw. So the two are very different in interpretation. Having said that, at this, if you have an n-dimensional parameter space, even if you have mapped out the entire n-dimensional distribution, which you will have done by doing this, you cannot plot n-dimensional distributions. You can only plot 1, 2, or maximum 3 dimensions at a time. So how do we eliminate the parameters we are not interested in plotting? We marginalize them out. We integrate them out, those parameters. So the general prescription, again, is if you say that if you have two parameters, theta and phi, and you're only interested in the marginal distribution of theta, what you have to do, you have to integrate phi out from the joint posterior. And that will be an integration that you'd have to do normally, except if you have the MCMC, all you need to do is simply count. You replace integrals by counting. Let me go here. So in other words, for example, here's an example from a very non-Gaussian distribution, as you can see. This is a case not involving cosmology, involving supersymmetry. I don't have the time to go into the physics here. Just take this as an example of a very non-Gaussian distribution with nasty multimodal regions. There are two parameters here. The joint posterior is on an 8-dimensional parameter space. And what you can see here, those are samples. Those are equal weight samples from the posterior distribution whose density reflects the posterior density. As we can see here, there is a region of higher posterior density, and then it fades away in this direction. There's another island of higher posterior density down here. There's another one up here. And now, if I'm interested in, say, one-dimensional marginal posterior distributions for each one of these two parameters, well, all I have to do, for example, to get the marginal for this parameter here, m1/2, I can just bin my parameter space in a suitable number of bins in this direction. And then because those samples are by construction due to the MCMC distributed according to the posterior distribution, all I need to do to compute the marginal integral is to count how many samples fall in each bin. So for example, in this case, if I marginalize out the y direction, in the first bin, I count how many samples I have in this bin, and that gives me this value here, this first bin. Then I go, no, sorry, that's down here. It gives me this bin here. Then I go to the next bin and I count, and I get this bin, the next bin, and I count, etc. And then what I get is a histogram, which is a numerical approximation to the full marginal posterior. And so the bottom line is that once you have the MCMC samples, integration is easy. You don't need to integrate. You only need to know how to count. And once you've done that, then in the Bayesian case, what you typically do, you will report credible regions. So in this example, here's a one-dimensional marginal posterior, and the 68% credible region, say the shortest interval credible region is the one that encompasses 68% of your samples, coming down from the top. So you start from the top, and then you start coming down until you hit 68% of your samples, and that's going to give you your 68% shortest credible region. And that's not a unique prescription. You could have symmetric credible regions or one-tailed credible regions if you had only an upper limit or a lower limit and so on. But the shortest interval is one that's often used. And I know that Tom has already covered the important difference between marginalization and maximization, say profile likelihood method, 20 cents. I don't want to cover it again. I just want to reinforce the message. Frequentist, profile likelihood method, and Bayesian marginal regions only agree in the simplest of cases, and they do agree in the Gaussian case, but in general, they will not give you the same result. And they should not give you the same result, because profile likelihood and marginal posteriors are actually two very different statistical quantities with different meaning. And so there's no reason why, in general, they should give you the same result. But remember, if you're looking at cases such as this, everything is easy and simple, and you can do whatever you like, basically maximization or marginalization, everything is giving you the same result for a Gaussian case. If you're looking at something like that, where you have very non-Gaussian distributions and nasty multimodal distributions, then what you do really matters, and the result, the scientific result of your inferences can be strongly dependent on the approach that you take, whether you are maximizing, whether you are marginalizing, and which priors you choose. And so some problems are nasty like that, in which case do not simply take your result of a Bayesian posterior blindly without, for example, doing a sensitivity analysis, without checking the influence of the priors, and perhaps even checking whether a likely result is very discrepant, because that points to the existence of strong volume effects that you'd like to understand. Before I move on, let me give a quick example, if I can find it. I just want to give you a very quick example of a nasty distribution like that, if you can find it quickly. Just a second, if I can find it in the next 30 seconds, I'll show it to you. I'll show it to you later. It doesn't matter now. I don't want to waste time looking for it. But there are examples where really your scientific result will depend very strongly on your assumptions and what you use, and you want to be aware of that. I'll show it to you after the break. Okay, to conclude this part about MCMC, move on to the supernovae. I again want to flag a few practical aspects. There are many MCMC algorithms. Metropolis Hastings, Hamiltonian sampling, Gibbs sampling, reduction sampling, mixture sampling, slice sampling, many more. And so each one of them is tailored to specific cases and specific difficulties in sampling certain kinds of distribution. The simplest one, arguably one of the simplest, is the Metropolis Hastings algorithm that work well in simple Gaussian cases of moderate dimensionality. If the problem is more involved, higher dimensional, or has got multiple distributions, then Metropolis Hastings might not be the best choice for you. Just be aware that there are many other ways of doing the sampling, and Metropolis Hastings is but the beginning of the story, not all there is. There's much more out there. So if your problem is nasty, make an effort to use a more powerful MCMC methods. And by nasty, I mean something from Gaussian, with heavier tails than a Gaussian distribution, possibly multimodal, generous Cs, and or high dimensional. And by high dimensional, I mean thousands, hundreds of thousands of dimensions. The Metropolis algorithm, I expect you have covered it. I'll just remind you what I mean by Metropolis. Metropolis 1954, so not exactly a new algorithm. The pseudocode is 4 lines long. So it's a very simple algorithm whereby you pick a structure location in space and you compute the posterior density there with P naught. Now, you propose the move in parameter space by picking a candidate new location theta c according to a proposal density Q, which is only allowed to depend on your current location and on your candidate point. This right here should actually look like that. This should be a C. Choosing the proposal density is crucial in ensuring that your exploration of parameter space is reasonably efficient. So you don't want your efficiency to be too high, because if you accept too many steps, you're not moving enough, and so you're under-exploring the tails of your distribution. You don't want the proposal density to be too large, the proposal acceptance rate to be too small, because otherwise that means that you're moving around, your steps are too large. So choosing Q is a little bit of an art, and there are other ways of doing that in practice. But then what you do, you evaluate the posterior density at the candidate point, and you accept it with probability given by the minimum of the ratio between the probability densities of the candidate, the point where you are at the moment, and 1. What this prescription means is that if the candidate point has got a higher probability, that's to say PC is larger than P0, then you always jump. You always accept a better point. But occasionally, you will also accept a worse point with probability proportional to the ratio, the probability of the new point to the current point. And that allows you to explore the tails of the distribution. You not only crawl upwards into the posterior, you also go downwards sometimes to move around in an appropriate random fashion. If the candidate point is accepted according to this criterion, then you add it to the chain and move there, and you loop back, go back here. If the candidate point is not accepted, then you count the current point once more, and you stay there, and you try again. So that's the Metropolis algorithm in a nutshell. Very quick, because I know that you've already seen it, so I'm not going through more details. Hopefully this just reminds you of things that you already know. Okay, in practice, especially if you end up using packages like Cosmology and other available packages in Python and whatnot, I just want you to be aware that convergence, that's to say ensuring that your MCMC is correctly sampling for the full target distribution, is a big issue, always. Never underestimate it. And so achieving good convergence and mixing, meaning that all of the chains are seen in the same parameter space, can in general be tricky, and you should be very careful in trying all the tests and think of to see whether your chains have converged. There is no fail-safe way of telling whether you have converged. You can only strengthen your knowledge that you have not failed to converge. There is no way of actually being sure. So there's a bit of black magic involved and of experience in this. And so successful MCMC remains a little bit of a black art in a sense, and just a few things that you want to watch out for: burn-in time, mixing, autocorrelation. And again, I refer you to references at the end of this presentation for details. Just in very short summary, burn-in, the period at the beginning of your MCMC where the chain is not yet sampling from the target distribution, still trying to look for the highest region of the posterior. And so you want to discard this initial period because that's not sampling from the target distribution yet. This is fairly easy to do. Here I'm plotting 4 example chains, and I'm plotting minus the log posterior, which is, or a flat pile, this would be just chi-squared, twice the chi-squared, as a function of step number in the MCMC. And what you can see is that at the beginning, the posterior probability density is very small. That's to say the chi-square is very large. So you start off in the wrong region in parameter space, but then quickly the chain converges to the good region. So this number drops, and see that when the chain is starting to sample from the target distribution, it's moving around nicely up and down in this fashion here. So what you want to do, you want to plot this quantity as a function of time and then chop off the first bit, the bit where it's not sampling from the target distribution yet, which I've chosen to be this red line in this case. So burn-in is simple. Mixing refers to the case where you have multiple chains, which is usually a good idea, starting from different regions of parameter space, and you want to see them converge to sample from the same region of parameter space. And so that means that they've all, despite the fact that they've started from different corners of the parameter space, they've all found the same peak of the posterior density. So here you see a cosmological example where we have 6 parameters, and I've run 4 chains which are colored lines, and the vertical axis gives you the step of the MCMC. And you can see, for example, in this plot, that 4 chains have started in 4 very different regions of the parameter space, but then they've all nicely converged to the same region of parameter space. And after the burn-in, they started to sample from the target distribution in the same place. So that again is a good sign, shows that you're converging. It does not guarantee that there isn't another region in parameter space, that none of your chains are same, but at least it says that the chains that you have seen the same region. And then there are more sophisticated tests looking at the power spectrum of the chain and the autocorrelation function of the chain and so on and so forth, which I don't want to cover in detail. I just want to point you the fact that there are many things you can do and many things you should do to make sure that your chains are a fair reflection of your target distribution. Okay, that's all I want to say about MCMC and parameter constraint from in general. Before I move on to the supernova type 1A example, are there any questions? Okay. Until the break, I want to briefly introduce the supernova cosmology case. I'll try to do it all in the next hour, so we have the last hour dedicated to cosmological Bayesian model selection. Again, a very brief introduction to supernovae. So supernovae are stellar explosions. And supernovae are divided in 2 classes, effectively. One is the core collapse supernovae, where we have a large star, typically of many times the solar mass, which burns away all of its elements. So it goes through hydrogen, helium, carbon, all the way to iron. So that this is for the core collapse supernovae. We're talking about the ones that have masses above 8 solar masses that will burn everything until they get iron. At which point, as you remember from your nuclear physics courses, nuclear fusion does not release any more energy past iron. It becomes an exothermal process, which means that in order to fuse iron into pure elements, you need to supply energy. Basically, you're running out of fuel. And so when that happens, the energy that was being emitted by the fusion process that was counteracting, balancing gravitational collapse is no longer available, and that triggers a core collapse of the supernova, which essentially is a thermonuclear explosion that emits a very large amount of energy of the order of 10 to the 51 Earth. Now, whatever this large number means, compare it with the luminosity of a typical galaxy, about 10 to the 44. And so this is a large amount of energy that can, for a brief amount of time, outshine an entire galaxy. A lot of this energy goes into neutrinos, which we do not see, but there's a lot of energy going into photons as well. It means that we get high luminosity explosions that can be seen from far away in the universe. This plot, this example here gives you an example of a supernova going off in a relatively high redshift galaxy. Now, there are different kinds of supernovae. Supernovae are classified in types. So supernovae type 1 are supernovae that have no hydrogen lines in the spectrum, while supernova type 2 contains hydrogen in the spectrum. And of particular interest for cosmology are supernovae type 1a. So type 1 is further subdivided in type 1a, and type 1b, and type 1c. Type 1a is characterized by the presence of strong silicon-2 ionization lines at the wavelengths of 6,000 angstroms, while type B do not have silicon. And the important part, the only thing that we need to know about the astrophysics of those systems is that it's widely believed that the supernovae of type 1a are coming from a different formation mechanism. In other words, they are not core collapse supernovae of the kind that I just described. What they are the outcome of a carbon-oxygen white dwarf closed binary system, which could be a binary system like this one, where we have a single degenerate star, a single white dwarf that accretes mass from a companion star, perhaps a red giant, that donate mass through a bridge, essentially, that allows the white dwarf to accrete. Or it could be a double degenerate scenario, where you have two white dwarfs in a closed binary orbit that eventually coalesce in a bigger star. So there are observational clues to support either of the two mechanisms, and it could be that the type 1a supernovae that we see in the universe are effectively a mixed family that come from both types of formation histories. We don't know. But the point is that, however this happens, the white dwarf is able to accrete mass above what is called the Chandrasekhar limit, which is 1.4 solar masses. That's the limit where electron degeneracy pressure in the white dwarf, which is the pressure that's providing a counter pressure to gravitational fall, is no longer sufficient to stop gravitational collapse. So you've got too much gravity on a too compact an object for the object to be supported by even electron degeneracy pressure. And so that means that the star, there's this collapse, gravitational collapse, and all of this gravitational energy gets converted into a thermonuclear explosion, and you get a big explosion of the star. So, however the however this might come about, however the supernova type 1a explosion comes about, the point is that there is this limit mass, the Chandrasekhar mass, which is the limit past which you get type 1a supernova, which is roughly the same in all scenarios, whether it's single degenerate or double degenerate. And that means it's plausible to expect that all supernovae type 1a will have roughly the same intrinsic luminosity. And that means you can use them as standard candles. Remember what I told you yesterday about the dependency of luminosity distance with redshift and the dependency of this curve on the value of the cosmological parameters. Here is the examples. So the idea is the following in a nutshell. Let me just find my notes. The idea is the following. Here we have our supernova going off and photons all around it with very high luminosity. So luminosity L of the supernova, and then we have the angular distance dl squared, and so L divided by 4 pi dl squared by definition of luminosity distance gives us the observed flux, F. So the idea is super simple. If we can observe the flux on Earth, and we know that all supernovae have the same luminosity, then we can work out the angular diameter distance at that redshift, and then we can work out the cosmological parameters. What's that? Of course, we might not know the absolute luminosity exactly, but it doesn't matter. As long as we know that they have all the same luminosity, we cannot know what is the absolute distance supernova, but we can measure relative distance between them. So if we have them spread over a range of redshifts, we can measure the change in luminosity distance across redshift, and then it's a question of anchoring the relationship with low Z observations. And so this relationship is valid up to an overall constant, which is set by the absolute luminosity functions. Okay, then of course in astronomy or astrophysics, we look at we usually talk about magnitudes. Apparent magnitude is, for historical reasons, defined as minus 2.5 log 10 of the flux, which is more than. Yeah? The absolute magnitude, capital M, is the same quantity but evaluated for the flux that you would see at a fixed distance of 10 parsec on the object. And the distance modulus mu is the difference between the apparent and the absolute magnitude. And from these definitions, you can just work out that the ratio of the fluxes for an object at distance, luminosity distance dl, that's the flux that you get from that object compared to the flux that you would get from the same object at 10 parsecs. You can do the math, and you can find that the distance modulus defined as the difference in apparent absolute magnitude for a wave band, for a band X, where X represents the band in which you're making observations, B band, R band, and so on, depending on your filter and your telescope. This mu is just given by this simple expression here. It's 5 log of dl expressed in megaparsecs plus 25. Okay, so in other words, when we're talking about supernova, I'm going to talk a lot about mu, the distance modulus of those objects. The distance modulus is nothing else but the log of the luminosity distance effectively expressed in the right units, up to a constant, which is just the 25, just down to definition of magnitude. In fact, we are measuring luminosity distances in megaparsecs. Okay. So now the program I want to do the next hour is to build on this and on the statistical methods that we need to carry out this program. Namely, what do we need to do this determination of distances from supernovae type 1a observations? Now you will know that this program has been highly successful in cosmology, Prize for Physics 2011, if I remember, because the supernovae type 1a observations in 1996 and onwards have shown that 1996, I think, and onwards have shown that the luminosity distance was such that it implied the existence of a cosmological constant. Let me conclude this part just by showing you the famous plot. This is the plot from Permuter et al. 1999. So what you see here is the V-band magnitude of those objects. You can think of this as distance modulus, effectively, as a function of redshift. So you can see here there's a bunch of supernovae at small redshift, and then there is the outcome of the School of Cosmology project observation, which they were able to get 20 or so objects at high redshift, right, 0.4 to 0.7. And you can see here, overplotted to these objects, the apparent magnitude, or say the distance, the luminosity distance you expect in the case of different cosmological parameter choices. For example, this is a model where the universe is purely of a cosmological constant, that's 50. This is a universe which is flat, but only matter. That's a universe which has, it's a closed universe with a negative cosmological constant. So, and the point is that, those observations are very difficult to make. So you can see there are large error bars, and there's lots of technical and sophisticated statistical details that has to go to making this kind of plot. And can't really do it by eye anymore. When you can see that they kind of lie up in the part of those lines, you can't really do the statistics by eye. You look at the residual plot down here, you will see that the universe which we live in, which is 0.28 matter 72 cosmological constant, is indeed, at least by eye, in this, it looks like a better fit than the alternative universes. But you can see that the difference in magnitude is small. The difference of the order between this cosmological model is of the order of few tenths of the magnitude. So you really need to calibrate those objects. You really get the distance modulus right, in a few tenths of a magnitude, able to distinguish between these cosmological models. And that is the entire supernovae type 1a program. And it turns out that there's lots of interesting statistics in doing that, and we'll explore some of it the next hour. Questions? Okay, so if there is no questions, we can adjourn for 5 minutes until 11 o'clock. Okay.